Okay, thank you, everyone. We are ready to start with the afternoon session of invited conferences. The next speaker is Professor Reina Natividad Rangel, and allow me to read the resume. It is in Spanish. Allow me. Okay. Professor Reina Natividad Rangel is Spanish, es doctora en ingeniería por la Universidad de Birmingham, en Inglaterra, ingeniería química, ingeniería química y maestría en metalurgia.
¿Dónde está Oscar? Ahí otro micrófono.
Ok. Está muy chiquito aquí el texto. Ingeniería química y maestra en metalurgia y ciencia de los materiales por la Universidad Michoacana de San Nicolás de Hidalgo, profesora e investigadora de la Facultad de Química de la Universidad Autónoma del Estado de México, UAM, desde 2005. Su trabajo le ha merecido varios reconocimientos y distinciones a nivel institucional, estatal y nacional, entre los que sobresalen los siguientes: miembro de la Academia Mexicana de Ciencias, ESMI 3, 2024-2028, nota laudatoria, UAM México, Estado de México, reconocimiento por la Universidad Autónoma del Estado de México por contar con 3 títulos de patentes, premio Scopus Elsevier 2023, Cátedra Marcos Mosinski, mención honorífica, Premio Nacional de Ciencia y Tecnología en Alimentos, Premio Estatal de Medio Ambiente, Beca a la Excelencia Académica, Universidad de Birmingham 2000 a 2004. Su trabajo ha contribuido al aprovechamiento de residuos como el CO2, aceites para la obtención de combustibles, y a la intensificación de procesos para remediación de cuerpos de agua. Ha contribuido a la ingeniería química y ambiental a través de la publicación de 115 artículos científicos, con un número de citas de 3.506, con un H-index de 35, 25 capítulos de libro y formación de 16 doctores y 31 maestros en ciencias, y de 29 licenciaturas en ingeniería química, 3 patentes otorgadas por el INPI. Ha realizado estancias de investigación en universidades como University College of London y University of Birmingham del Reino Unido, Thomson Rivers University de Canadá y Universidad Michoacana de San Nicolás de Hidalgo en México. Ha contribuido a fortalecer la infraestructura de la Universidad Autónoma del Estado de México mediante numerosos proyectos de investigación financiados por CONACYT, COMECYT, CEP y la Universidad Autónoma del Estado de México. Divulgación de la ciencia, más de 150 presentaciones nacionales e internacionales, pláticas y pósters. So this is the huge resume of Professor Natividad. The plateau is yours, and the presentation is photocatalyzed CO2 valorization. So go ahead, please. Thank you so much for being here.
Está apagado, creo. El
microphone is off.
Hello?
Yeah.
No. Okay, I was testing you. Okay, is it okay in Spanish or in English?
So we prefer in English, but I don't know if the audience...
Is it okay in English? Yes?
Okay.
Everyone? Okay, fine. Thanks a lot for the introduction. So we'll be speaking today about the photocatalyzed CO2 valorization. This is a research that we are conducting at the Chemical Engineering Laboratory at the Joint Center of Sustainable Chemistry, UAM, in Mexico. This is actually in Toluca, well, nearby. This is the outline of this presentation. First, I'll be giving you an introduction to CO2 valorization, and photo reduction. And then I'll be speaking to you about two strategies that we are exploring at the Chemical Engineering Laboratory. And this is these two strategies are studying the types of catalysts and types of reactors. Then I will be presenting results of the characterization of the catalyst and of the effect of different reaction conditions on the production of a compound that is of our interest, and that is formic acid. And then conclusions and acknowledgements, and if there is some time left, I will be introducing the Chemical Engineering Laboratory, but only if there is time. So CO2 valorization, well, carbon dioxide is a residue that is not doing very well for the climate change. And although it's necessary, here in the image, you can see all the greenhouse gases like methane, carbon dioxide, well, there are others. And actually, CO2 is not the one with the highest environmental impact, I mean, in terms of heating effect, but it's the gas that we are producing the most with all of our activities. So it has been taken as a reference. And then there is a necessity to capture the CO2 or to transform it, in other compounds. And that strategy, the transformation of carbon dioxide into other compounds, is called CO2 valorization. That means that that residue, the carbon dioxide, can be taken now as feedstock of another process. So what are the products of interest? These are formaldehyde, mind the Spanish, sorry, formic acid, and methanol, ethanol, methane. And how do you obtain those compounds? Well, by applying a chemical reduction of the carbon dioxide. Of course, there is the reverse reaction or the opposite, and that is oxidation. And through this reaction, you can obtain carbon dioxide again, which is very good in terms of fuel cells, for instance. And so how to do this? Well, there are different processes like electrochemical, photocatalytic, thermal, or hybrid processes like photoelectrochemical, thermal electrochemical. But today I'm gonna speak only about the photocatalytic process. And actually, the process can be conducted in the gas phase or in the aqueous phase, in the liquid phase. Today, I'm gonna focus on the liquid phase. So I'm not speaking about the gas phase photoreduction. That is another topic. And so I've been concentrating my efforts in the lab to study the CO2 photochemical reduction in aqueous phase. So I want to speak to you about that today. Oops. So why is formic acid of interest? Well, it used to be, it's an organic compound, and it used to be only used as a food additive. But then lately, in the last decade, it has become important to be used in fuel cells. Actually, there are some fuel cells that are called direct formic acid fuel cells. These ones. So in those cells, they are mainly electrochemical. The formic acid is oxidized at the anode, and that produces the hydrogen, and it also produces CO2, well, in the other side, and that CO2 can become, again, formic acid. So you are closing a loop there, and that is very important in terms of sustainability and circular economy. So formic acid is a very important compound, methanol also, but formic acid is of rising interest, and I'm going to focus today in the production of formic acid. Although we are also producing methanol, but I'm going to focus on that molecule. So this is now it has become kind of general knowledge, this scheme. So for the photocatalysis, you need a catalyst that is a semiconductor. For those not very familiar with photocatalysis, well, in a semiconductor, there is this energy band gap that is not really physical, but it's a difference in energies between the conduction band and the valence band. So generally speaking, when a photon of light hits an electron and excites this electron, then you leave an energy hole behind, and that energy hole has the energy to oxidize the water, for instance, and also to produce the hydroxyl radicals. And this is the part where usually the most of researchers have focused in photocatalysis. Why? Because these radicals are highly oxidizing. So you can treat water or eliminate organic compounds from water by using this species. However, there is the other part, the electron part, that most of people have forgotten, and then this is quite useful for reductions, for chemical reductions, right? And then, although this event is about advanced oxidation processes, you can't actually forget about this. If you are doing an oxidation in this part, you are definitely producing this electron. So one of the problems in advanced oxidation processes by photocatalysis is the recombination of the electron. Why? Because then you are not using these energetic holes, and you are producing less of these hydroxyl radicals, right? So, but then this electron becomes very important for the CO2 photoreduction. One of the challenges in this area is the activation of the catalyst by visible light. Why? Because the catalyst, the most applied photocatalyst is titanium dioxide, and this photocatalyst is only activated by UV light. So in terms of sustainability, we are heading to processes activated by solar light. And solar light or sunlight only has 5% of UV light. So if one wants to conduct these processes under sunlight, you must develop photocatalysts that can be activated under sunlight. Otherwise, we will be slaves again of energies, other energies, because we need lamps to produce that UV light. And then, so this photocatalyst, the titanium dioxide, presents that challenge. There are several strategies to overcome this problem, and one of them is the doping with metals that I'm actually presenting. I'm going to present you results with titanium dioxide doped with copper, but also we have been assessing other photocatalysts. There are actually quite old catalysts, but are quite new photocatalysts. So I'm going to present that. So in this sense, the formic acid is produced by using the electrons that you might be thinking where the carbonic acid comes from. Well, it comes from bubbling the CO2 into water, and then that starts a change of reactions. where it's formed the carbonate and then the carbonic acid. And then this carbonic acid becomes the main species that we are actually reducing by combining with the electrons in the conduction band. And that produces also the formiate radical, and then by proton transfers, we can obtain the formic acid. So at the end, the formic acid production will depend on all the pool of chemical species that we are producing, either by UV light or either by visible light. And look, the hydroxy radical is going to become really important, because if we are producing an organic compound, what is going to happen here? Well, it's going to be oxidized also. So this becomes really important, because at the end you are going to get a balance on the chemicals produced in the produced chemical species. And also that hydroxy radical that is essential for the advanced oxidation processes becomes essential for the carbonate activation. So this is the catalyst that I'm going to talk to you about. The first one is copper on titanium dioxide, and then the photocatalysts. There are new photocatalysts, although are old catalysts for thermal catalysis, are the pillar clays. Pillar clays doped with aluminum and copper, and with iron and copper. What are pillar clays? Well, chemically speaking, they are aluminosilicate layers. Here, you can see this. And then by ionic exchange, we are introducing ion species here, like pillars, chemical pillars, and then copper oxides. By XPS, we have proved that those species are the ferrous oxide, the ferric oxide, and magnesite, and also the cuprous and cupric oxide. What are the advantages of these photocatalysts? Well, I'll be proving to you the different advantages over titanium dioxide from the photocatalysis perspective. But all of them are semiconductor have semiconductor properties, and they facilitate the CO2 chemisorption, mainly the copper species. Okay, types of reactors. This is the typical semi-batch reactor where there is the water or another solution where the carbon dioxide is being bubbled. And here, sorry, this is the typical semi-batch stirred-tank reactor. And here, the species are all the time in contact with the gas and the light. But the capillary reactor that we developed at the chemical engineering laboratory, and that we obtained the patent for that, is this capillary reactor. I'm going to show you in a minute how it works. The interesting about the capillary reactors is the different gas flows that you can obtain inside the capillary reactors. Why is this so special? Because every one of these flows gives you a different hydrodynamics, and that different hydrodynamics impacts the selectivity of the products, meaning the product distribution, right? So the most wanted one is this one, the Taylor flow, and all these depend on the relative velocity of gas and liquid. This has been used for hydrogenations mainly, and for CO2 reduction, but in the gas phase. In the liquid phase, we were the first ones in the world testing that reactor for that reaction. For this, for the copper and titanium dioxide catalyst, we tested these variables to try to understand the reaction, and this was the a response variable, which was the formic acid yield. Here is the photocapillary reactor. It consists of a capillary which can be so you have to use a light source. This is the visible lamp that we use, but you can also place a UV light lamp here. And then you have here a T connection where you are feeding the CO2 gas and the liquid phase, and they enter to the reaction zone. And then here is a container where is again taken by a peristaltic pump and recirculated. So at the end, it's a batch reactor in terms of the inlets and outlets, a semi-batch reactor, but it doesn't have an steering, or at least not a macro steering. Each of this is the liquid phase here, and this is the gas phase. Interesting of this flow is that every one of these liquid slugs is a perfectly mixed reactor, but small ones. So you have gas followed by this liquid phase, and then the catalyst can be in powder, which gives you another way of working with that reactor. But you can also coat the quartz capillary. You can coat it here on the walls, and then you don't have to separate the catalyst. But you must be very careful if you're going to apply these reactors in photocatalysis. The coating must be transparent to light, to the radiation light, either visible or UV. And that is one of the challenges in these photoreactors. Can you play the video? Oh, there is nobody in the support. Okay. Well,
yeah, give us a minute, please.
Here, there is in the bottom, if you can play this. Yeah. There is also the proof the advantage of the reactor in terms of selectivity. We have compared the results of this reactor with the typical steering reactor. So this is the batch reactor, the semi-batch reactor that we use. There is the bubbling. If you try to do this reaction, the gas diffuser characteristic is essential because of the gas bubble size and also the gas flow. And one might think, one that is not an engineer, might think that if you input more gas, that's going to be better, but it's not because of the residence time. You need a low CO2 gas, CO2 flow, so you can obtain a proper residence time so the CO2 can dissolve into the solution. If you input a lot of gas, or the convection is higher, the residence time is lower, and then the CO2 concentration in the solution is low. So be careful with this. It's a very important variable. So the flow that we are applying is only 9 milliliters per minute. So these are the results of the characterization. By X-ray diffraction, we proved that we had obtained the photocatalytic active phase of the titanium dioxide that most of you in photocatalysis must know that is anatase, right? And then we obtain also the band gap energies. Here is for the titanium dioxide that we prepare in the laboratory by Soldier method. So we obtain a pretty close value to the commercial to the commercial catalyst. And this one was 3.2, near to 3.2 electron volts. But then when we added the copper, we obtained a decrease and it went down to 2.6, around 2.6. So remember that we added copper for two reasons. One, to promote the commercialization of the carbon dioxide or carbon species, and also to decrease the energy band gap so it can be activated by sunlight. By transmissional electron microscopy, we obtained the interplanar distances that prove that, that there was anatase. And then by XPS, we also obtained the coordination of the titanium and copper. And that was one of the catalysts. The other catalyst that I'm going to present in results is the aluminum copper pillar clay. In this case, these were the studied variables. And here I'm showing you how the aluminum silicate layers are formed. And here in the interlaminar spaces, we conduct an ionic exchange. There is sodium or calcium, and then we input metal cations like copper or iron. And the result is this. And again, we focus on the production of formic acid, although we also obtain methanol and acetic acid. Here you can observe the original clay was bentonite, and this is the typical diffraction spectrum of the bentonite. And you can observe here, after the pillaring, the signal becomes almost disappear, and it displaces to lower 2 theta degrees, and this is indicating that the pillaring process was conducted properly. And then by XPS, we observe the oxidation states of the copper, and we observed that it was cuprous and cupric. And then with this system, we tested the effect of the copper content, but very important, we also studied the effect of the sodium hydroxide concentration in water. We observe all this mixture of phases, ferrous, ferric, magnetite, and cuprous and cupric. Very important, and there is something that usually from the point of view of photocatalysis, we usually don't study it, and that is the oxygen vacancies. Yes, there are studies related to that, but it's not like standardized in the photocatalysis area. But well, we observe here, and please pay attention to this. The higher the content of copper, the higher the oxygen vacancy. And then you later will be able to correlate that with the production of formic acid. Here we also, and this is also usually conducted for thermal catalysis, but not for photocatalysis. And you can observe here that the Bronsted acidity increases with the copper and ion content, and the Lewis acidity also. Here is a characterization with this catalyst with the highest copper content that was around 4%. We observe a band gap energy of 2. This is already indicating us that this catalyst was going to work properly with visible light, which actually did. Here are the results that we obtained in the production of formic acid. Here is for copper over titanium dioxide with UV light. You can observe here the effect of copper, which was pretty good. Here, for those who are starting to to do your studies in photocatalysis, the catalyst loading is a very important variable. In this case, in photocatalysis, more doesn't mean better. In this case, it did, but why not? Because it becomes the highest the catalyst loading produces this screen effect, which affects the photons reaching the higher distance from the axis of the reactor. So be very careful about this variable. We obtain here that with 1 gram per liter, there was the highest concentration. We obtain also the highest concentration of formic acid. However, this concentration, this catalyst concentration is quite high compared to the catalyst that we use. This was the proof that it works with visible light. Here, it was the catalyst was immobilized onto the capillary walls, and here it was in powder. So you can observe here, you can observe the production, but it's still better with slurry catalyst. Here is the reaction pathway that we postulated with that study. We observed the methanol, the acetic acid, and the formic acid. So see, this is the proof that CO2 can be valorized by this process, although was a challenge, increase the yield of those compounds. And with aluminum copper pillar clay, look here, the low catalyst concentrations that we use with this catalyst. So the best catalyst loading, the best in terms of formic acid production was 0.05 grams per liter compared to the 1 gram per liter that we use with copper over titanium dioxide. So, and you can see here the productivity of formic acid, acetic acid, and methanol. In methanol, we were already in the order of millimoles, right? You might think that it's quite low, but in the context of production, of the production of these compounds, we are quite competitive in photocatalysis, okay? So this catalyst is definitely active in visible light. Look, the amount of methanol that we obtain with visible light. So this is a promising catalyst, actually. And we also added some molecules to try to understand further the mechanism. This alpine and methanol are usually added to scavenge the hydroxyl radicals and see the importance of those radicals. Well, it was surprising, but we didn't observe any difference here. While with glycerol, we observe an important difference. So in this case, this glycerol, we did a separate study on the glycerol oxidation, and we observed that the glycerol oxidation was not only producing formic acid, but it was also producing protons and these hydrogen radicals. So this is telling us that the main species, or the most important species that we should focus on, are the hydrogen or the protons. These are the results with iron copper pillar clays. And here is, you can observe the effect of using sodium hydroxide. What is doing the sodium hydroxide? Well, the sodium hydroxide is altering the chemistry of the solution chemistry. With sodium hydroxide, we are accelerating the production of carbonic acid. I'm not presenting the results, but we studied that reaction in a separate way. So again, the higher the content of copper, the higher the formic acid, And also, well, you can observe here that when you use the sodium hydroxide, there is actually not much difference between these catalysts, but there is an important difference when there is only water. And as I told you before, this has to be with the speciation in the solution, which here between a pH of 5 and 11, you have mainly the bicarbonate ion. Here you have the carbonate. That means at the beginning of the reaction with sodium hydroxide, you have mainly carbonates because you are working in this area here. But with water, you are working in acid pH. That means you are working here, and let's see, in acid pH, we have mainly molecular CO2. So actually in water, we are really conducting the CO2 photoreduction, while at a higher pH, we are doing the reduction or the chemical reduction of the carbonates and bicarbonates. I'm gonna skip this. And well, here, and I invite you to go to this reference. And we are proposing this reaction pathway where all the role of the metal oxides is acknowledged to produce. Look, you can even see here hydrogen peroxide. You might be thinking, where did the hydrogen peroxide come from? Well, it comes from the use of the light, and also it comes from the recombination of the combination of the hydroxyl radicals. So we detected we detected the presence of hydrogen peroxide, and of course it's working here together with all the other species to produce the formic acid. Here you can observe the role of the protons and the oxygen vacancies also. Finally, well, the conclusions is that copper over titanium dioxide works better under UV light, but the pillar clays that we have synthesized at the laboratory perform better under visible light. And the aqueous medium promotes the electron-proton transfer. How did we conclude that? Well, with the Bronsted and also with the Lewis acidity. And then the photoreduction of CO2 under alkaline conditions, well, proceeds via carbonate and by carbonate ions. This was observed or concluded by the pH study. And the metal combinations enhance the charge separation. The glycerol favors efficient hydrogen transfer to photogenerated holes. Glycerol, why we chose glycerol? Because it's another residue. Actually, we have another line, a research line. There is some biodiesel production, and a main byproduct of that reaction is glycerol. And well, the role of mineral clays is not only as a catalyst support for conversion of CO2 into fuels, but they can also act as co-catalyst. And well, the pillar clay systems stands out to produce formic acid, and that is already in the context of photocatalyzed reduction of CO2. And I want to acknowledge the contribution of my colleagues and students working in this project. And finally, thank you for your attention.
Okay, thank you for the kind presentation. And now we open the session of questions and answers. Anyone? Yes, go ahead. Allow me.
Thank you for such an interesting talk. I was wondering about the method for this, preparing your composite catalyst. I mean, copper or aluminum on titanium. Which method did you use?
Okay. I have a slide here. We say in Spanish, I wasn't prepared, but here you go. Ah. Okay. It's a ionic exchange. So we prepare these solutions, and we with these salts, and so we add this to change the pH, and add it dropwise to the bentonite, then filter and washing. And to be honest, this washing thing is one of the less sustainable stages of the preparation of this catalyst, because it takes a lot of water. Why? Because the conductivity must be below 5 microsiemens. So it takes a lot of water here. And then is drying calcination under these conditions. Here is the reference of this process.
Could you comment about the origin of your bentonite?
Pardon?
Bentonite. The origin of your bentonite is commercial bentonite?
It's commercial.
Is natural bentonite? Because there are in Mexico several mines of bentonite.
Yes, and actually the source is quite important. It's Thermo Fisher is a commercial one, and if you change of bentonite, the results are different. Yes, and yes, we're in trouble now because we have been able to import the Fisher bentonite. So,
But I remember that several decades ago,
wow.
one of the professors of the Institute of Chemistry worked also in heterogeneous reactions,
Okay.
and he obtained bentonite from Tehuacan, Puebla.
Okay.
And there are mines of bentonite there. He obtained large quantities of bentonite that he just brought to the Institute of Chemistry, made a lot of reactions there.
Okay.
And he also commented the same thing.
Yes.
Because there are also mines, I think, in Durango.
Mm-hmm.
And they are bentonites, but they are not behaving the same way because they contain different minerals,
Yes.
etc. That's why the reproducibility of this method depends a lot in the origin of the
Yes.
support.
Yes, you might want to get me a souvenir from Puebla now that you are doing
Yeah.
your sabbatical over there.
Okay, excellent. Another question?
In Spanish, if you want.
I
I'm okay with it.
have one.
Yes.
Could you talk about the quantum efficiency of your materials?
Okay, yeah. No.
Okay.
No, not at this moment. I wanted you to say, can you speak about the quantum efficiency of the reactors? Because that I can talk about that, because we have actually conducted measurements, and it's higher in the capillary reactor than in the stirred reactor. But about this photocatalyst, we haven't conducted the measurements yet.
Okay. And another question over here. Okay, okay.
Thank you too much for your presentation. It was very interesting. My question is, how can you solve the recombination? Because you mentioned it is a problem.
Yes, the charges recombination or the oxidation of the formic acid?
No,
Because, the charges recombination, the electron. Okay, when you dope a material with a metal like copper, it's the electrons or the copper can work as a trap for the electrons, and that is the reason for doping the titanium dioxide with metals. But another strategy is also increasing the oxygen vacancies, because those oxygen vacancies work as electron traps also. So, and how do you produce that? Also adding the metals. And so the higher the oxygen vacancies, you might observe a reduction in that recombination. And if you follow a reaction, if you're doing a photocatalytic reaction, a very simple way to observe the recombination is by an increase of temperature. If you observe that the temperature is increasing very fast or in a different way compared to the same reaction with another material, it might be, it might suggest to you that the recombination is being faster with that catalyst than with another. But physically, you do it by, you reduce that by adding metals or cations.
Thank you.
Okay, over here.
Thank you, Doctor. Thank you for your presentation. It was very interesting. My question is, you mentioned that use the bentonite as a support. So even you mentioned that it is used as a co-catalyst. So my question is how the bentonite could use or improve the elimination. And another question is why bentonite, which would be the difference of using bentonite or another aluminum silicate clay?
Okay, well, the way that we observed that it was a catalyst, it was because we conducted experiments only with bentonite, and we observed the reaction. The reaction is already conducted only by bentonite. The formic acid is increased, the concentration is increased when we added the pillars, the metal pillars. But then, well, there is that contribution of the bentonite. And how the second question was how the source or the composition of the bentonite could affect. We believe that is because of the acidity of the Lewis acidity that is changing. No, the other way around. Okay, here I have a table where you can observe the acidity of the for volume. Here, you can observe here the bentonite has this Lewis acidity and 0 Bronsted acidity. So if you change the source of bentonite, that means that it's going to have a different proportion or a different ratio of aluminum and silicium, and that for sure is going to affect these two values. So that we believe that would be affected, and then that affects the formic acid production.
Okay, more questions? I have another one.
Okay.
Okay. In this table, we can observe that you have roasted acidity on the surface, but is there a good explanation about why you can obtain carbon molecules having 2 or 3 carbons in the structure?
Yeah. Well, not sure if it's a good explanation, but. See, this Bronsted acidity means that you are producing a surface with a higher capacity to transfer protons, right? And as Lisa will show us, the production of protons is very important. So, where it was here. So if you are producing these protons are gonna react with these electrons, and with this formiate, it can be the formic acid, but also the presence of this bicarbonate can produce all these radicals, and also the production of methanol and formaldehyde, and the combination with these protons are going to produce this higher carbon molecule. So it's this by protons transfer and electron transfer mainly. That will be what we have at the moment. Yeah. So the challenge, I believe, is to control all these species.
Okay. We have more time for questions. For that, allow me.
Thank you. Thanks. Thank you for your presentation. What are the chemical properties that make copper and iron suitable use in catalytic process or another reasons?
Okay, I believe that is because of the basicity and acidity that give to the surface. In the case for the and also in photocatalysis, for the ability to give semiconductor properties to a material. So copper oxides and iron oxides are semiconductors. So that characteristic makes them good to be used there, and along with the acidity and basicity properties.
Okay, another question? No? Okay. So thank you very much for the kind presentation and a lot of work in your research. And allow me to end with this present for you.
Thank you very much.
Thank you so much for sharing the research with all of
Thanks a
us.
lot.
Thank you. And some announcements. Carlos Montalvo Romero is in the room, in the classroom, wherever. No? Okay, so I understand that Mitzi and Axel is right here, but we can move to the presentation of from Mitzi. Okay, and we can continue. Mitzi Naomi Camargo. Yeah. Come on. Thank you. Okay. Mitzi Naomi Camargo will talk about the degradation of indomethacin in gray water by electrochemical oxidation. So Mitzi, the plateau is all of yours. Thank you. Yes.
Hola, buenas tardes. Vengo de la Universidad Autónoma de Querétaro y les voy a presentar mi proyecto, que fue la degradación de indometacina en aguas grises mediante oxidación electroquímica. Estos son algunos de los contenidos que vamos a estar viendo a lo largo de la presentación. Y pues para comenzar, sabemos que una de las principales problemáticas ambientales es la contaminación del agua a través de contaminantes tanto convencionales como emergentes. Algunos de ellos son los fármacos, las hormonas, los productos de cuidado personal que no son degradados completamente en las plantas de tratamiento de aguas residuales, por lo que van a estar llegando pues a los cuerpos de agua y subsecuentemente a nosotros, ¿no? Entonces vamos a prestar mayor énfasis a los fármacos. Entonces, pues la indometacina es un fármaco antiinflamatorio no esteroideo que tiene la función de inhibir una enzima llamada COX-2 que se encarga de los procesos inflamatorios, por lo cual se va a prescribir para afecciones musculoesqueléticas, como lo es la artritis, la osteoartritis, y también es un antipirético. Entonces hay diferentes vías de administración, sin embargo nos vamos a centrar en la vía tópica a través de cremas y geles. Sin embargo, solamente hay un 20% de absorción a través de esta vía, por lo que los remanentes que van a quedar en la superficie de la piel van a ser excretados a través pues, de la ducha, del lavado de manos y del lavado de ropa, por lo que van a llegar a las aguas grises, las cuales tienen ciertas características. Sin embargo, una de las principales pues, es la presencia de surfactantes en un 20 a 10%. Estos surfactantes tienen la capacidad de modificar la tensión superficial, así como formar micelas y emulsificaciones, debido a que tienen una región hidrofílica y una región hidrofóbica. La región hidrofílica es aquella que les va a conferir la clasificación, ya sean iónicos, catiónicos, no iónicos, anfotéricos, y sobre todo nos vamos a centrar en los aniónicos, como el de sulfato de sodio, el cual se encuentra presente en diferentes detergentes de uso común, y el polisorbato 20, que se encuentra sobre todo pues, en productos de cuidado personal, debido a que son menos corrosivos o abrasivos. Entonces, pues bueno, se ha reportado ya que la indometacina puede llegar en concentraciones de 0.1 a 100 nanogramos a los efluentes de agua, y al ser un fármaco, pues va a estar conservando su actividad biológica, por lo que al entrar a los organismos va a estar inhibiendo esta enzima, COX, y lo que va a reducir es la producción de las prostaglandinas, va a causar estrés oxidativo, y también se ha visto que causa afecciones en cuanto al comportamiento, la reproducción y el crecimiento de ciertos organismos. Por ejemplo, en Dania rerio se ha visto que causa malformaciones cardíacas. También hay diferenciación sexual sesgada hacia machos por la inhibición de COX-2. En mamíferos, por ejemplo en ratas, el estudio que se hizo, se vio que hay sobre todo daños en el sistema gastrointestinal, ya que puede causar ulceraciones, e incluso en plantas se ha visto que hay alteraciones en los parámetros fotosintéticos y en metabolitos secundarios, por ejemplo la disminución de la clorofila B. Por ello es importante comenzar a buscar alternativas a los procesos convencionales, por ejemplo el uso de la oxidación electroquímica, que consiste en la aplicación de corriente eléctrica en un sistema electrolítico para oxidar en la superficie del ánodo. Hay dos formas diferentes, que es la oxidación directa, en donde se da la transferencia directa, valga la redundancia, de electrones en el ánodo, y también hay una oxidación indirecta en la cual se van a estar electrogenerando ciertas especies que van a viajar al seno de la solución, donde se van a estar degradando los contaminantes. Hay diferentes variables operativas que son importantes en la oxidación electroquímica, por ejemplo, la intensidad de corriente, el tiempo de reacción, la conductividad, el tipo de materiales de los electrodos, ya que estos van a estar jugando un papel en la quimsorción y la fisisorción, en cómo se van a estar interactuando con los electrodos, así como también otra variable importante es la composición del electrolito soporte y el tipo de contaminante. Por lo cual la hipótesis que nosotros planteamos fue que la activación del ion persulfato va a estar promoviendo la oxidación indirecta para la degradación de indometacina en agua, tanto en la interacción con los surfactantes como en un agua gris real. Y el objetivo general es evaluar la eficiencia de la degradación mediante la oxidación electroquímica en presencia de surfactantes. En cuanto a los objetivos específicos, el primero es determinar el efecto de las variables de operación en la generación de especies oxidantes. El segundo es evaluar estas variables de operación en la degradación de indometacina. El tercero sería validar el proceso usando una matriz real de agua gris. Y por último, hacer algunas pruebas de fitotoxicidad para ver la toxicidad, valga la redundancia, en un organismo modelo que es Fasciolos vulgaris. Algunas de las técnicas analíticas que estuvimos utilizando fue la cuantificación de oxidantes a través de titulación iodométrica, la determinación del radical hidroxilo a través de fluorescencia, espectrofotometría de fluorescencia, el monitoreo de la indometacina y el peróxido de hidrógeno a través de espectrofotometría UV visible y la determinación de la DQO. Les presento mi sistema. Está constituido por un reactor de 500 mililitros y dos ánodos de óxidos mixtos de iridio y rutenio, de óxido de iridio y óxido de rutenio, y tres cátodos de titanio que están dispuestos en placas planas en paralelos a flujo, También utilizamos una fuente de poder y una bomba peristáltica. Asimismo, añadimos un difusor de aire para estar promoviendo pues, la transferencia de masa. En cuanto a la cuantificación de oxidantes, nos dimos cuenta que desde el tiempo cero teníamos la formación de oxidantes e incluso cuando no aplicábamos corriente, pues teníamos una concentración considerable de estos radicales. Y esto se debe que al usar el persulfato de sodio como electrolito, pues se van a estar dando diferentes vías de activación, ya sea a través de la vía electroquímica o también a través de los electrodos, que sin embargo, o sea, si bien tendrían que ser inertes, pues estaban participando en la reacción. En cuanto a la cuantificación de los oxidantes, de los radicales hidroxilo, a través de la hidroxilación de la cumarina, obtuvimos de igual manera que había ciertas señales, incluso en el tiempo cero y cuando no teníamos presencia de la corriente, por lo cual pues es la misma explicación, la interacción que se da entre los electrodos y el electrolito que se estuvo recirculando. Lo siguiente que hicimos fue un diseño factorial 2 a la 4 para la formación de oxidantes, en donde obtuvimos una matriz con 16 pruebas experimentales, donde nuestra variable dependiente fue la concentración de los oxidantes en molar. Y a partir del programa Design Expert obtuvimos una ecuación polinomial, la cual nos ayudó a hacer un diagrama de Pareto para ver las contribuciones de cada uno de los valores. Aquí lo que obtuvimos es que la variable con mayor importancia fue la concentración del persulfato de sodio, y pues esto tiene mucha consistencia con los resultados que habíamos obtenido previamente. También hicimos un diseño factorial 2 a la 4 para evaluar la degradación de la indometacina. De igual manera obtuvimos una matriz con 16 pruebas experimentales y aquí la variable dependiente pues fue la remoción de la indometacina. De igual manera obtuvimos una ecuación polinomial y aquí lo que estuvimos variando fue el tipo de electrolito que estuvimos utilizando. Por una parte utilizamos el persulfato de sodio y el sulfato de sodio, y nos dimos cuenta que tanto la concentración del electrolito como el tipo de electrolito tenían gran influencia en la degradación de la indometacina, y esto se debe a la formación de los radicales sulfato. Lo siguiente que hicimos fue la evaluación de la corriente para la degradación de la indometacina. Aquí, a pesar de que no tuvimos diferencias significativas al hacer un análisis de varianza, al implementar un modelo cinético no elemental, conocido como Chanichú, nos dimos cuenta que la variable que mayor peso tenía era cuando teníamos 300 miliamperes, es decir que si aumentábamos la corriente teníamos menor degradación debido pues a las especies parasitarias que se daban. También estuvimos midiendo de forma independiente el efecto del flujo para la degradación de la indometacina. Aquí estuvimos variando y aumentamos el flujo de 73 mililitros a 500 mililitros y también implementamos un difusor de aire. Es decir que aumentamos el flujo a 500 mililitros, implementamos el difusor de aire y fue cuando obtuvimos mayores porcentajes de degradación. Y esto se debió a que también estábamos teniendo presencia del peróxido de hidrógeno. Ahora sí, pues en cuanto a la degradación de la indometacina en presencia de surfactantes, obtuvimos mayores degradaciones cuando teníamos el dodecil sulfato de sodio que con el polisorbato 20, y esto se debe a las interacciones que se estaban dando. Debido a que no teníamos la concentración micelar crítica, por lo que la indometacina se encontraba más disponible en el medio, a comparación de cuando estaba el polisorbato 20 a su concentración micelar crítica. Además de que el SDS, también puede formar especies radicalarias a partir de los grupos sulfatos que se encuentran, y el polisorbato 20 también podía encapsular nuestro contaminante haciéndolo menos disponible, y por ello podemos tener pues una menor degradación. Ahora sí, en cuanto a la validación en agua gris real, pues nos dimos cuenta que este proceso sí puede ser útil una vez que lo escalamos a una matriz real. Sin embargo, hay parámetros que aún hay que estar evaluando y se podrían pues implementar procesos previos o posteriores para tener aguas más idóneas, debido a que cuando hicimos la prueba tuvimos pHs muy bajos y pues esto no es muy favorable para los organismos, ¿verdad? También estuvimos haciendo pues las pruebas de germinación y crecimiento de Phaseolus vulgaris, que es el frijol común. Aquí tuvimos un control, el cual fue regado con agua. También tuvimos un control de indometacina, el persulfato a concentración de 5 milimolar a 50 milimolar y el efluente tratado, que si nos damos cuenta, pues desde aquí podemos observar que hay menor crecimiento y también hay mayor inhibición en cuanto al crecimiento de nuestra planta. Estuvimos midiendo diferentes parámetros, por ejemplo, el porcentaje de germinación, y era como lo comentaba, ¿no? Una vez que tenemos nuestro efluente ya tratado, tenemos menores porcentajes de degradación en comparación de cuando tenemos pues solamente nuestra indometacina sola. Y esto pues se podría explicar debido a que pues tenemos especies remanentes o residuales de lo que son nuestros radicales, y pues al final son especies reactivas de oxígeno y van a estar afectando el crecimiento de la planta. También estuvimos midiendo tanto la longitud y el diámetro. De igual manera, pues todos los parámetros fueron consistentes, tanto el diámetro como la biomasa fueron consistentes en que nuestro efluente tratado pues fue el que tuvo el menor crecimiento y pues germinación. Y cuando hicimos las pruebas de biomasa con el peso fresco y el peso seco, el peso fresco, que es este verde un poquito más clarito, podemos ver que no hay como mucha diferencia en cuanto a al peso a la biomasa, perdón. Y esto se puede deber a, más que nada, en vez de que haya una disminución de la biomasa, hay un estrés osmótico. Y pues ya, en conclusión, la oxidación electroquímica pues es un proceso eficiente para degradar la indometacina en presencia de los surfactantes. El proceso está sobre todo mediado por el radical sulfato. El SDS fue el que obtuvo pues mayor degradación en comparación con el polisorbato 20, y esto se debe más que nada pues a las cargas de cada uno de los surfactantes. En agua gris real obtuvimos un 33% de la remoción de DQO, pero pues es importante implementar otros procesos que sean pues un poco más amigables con los organismos. Y pues eso sería todo. Muchas gracias.
Thank you, Mitzi, for the kind presentation, and we open the session of questions. Any question for Mitzi? Anyone? Okay.
Hola, ¿pudieras explicar en la parte de los experimentos con las aguas grises? O sea, tú pusiste ahí el contaminante, ¿a qué concentración? Eso no me quedó muy claro. Y respecto a los tratamientos, solamente teniendo en el agua el analito, ¿cuál es el máximo nivel de eliminación? Creo que ese es el 90 y algo, ¿no? O sea, porque es mucha la diferencia, pero no sé, en el caso del agua gris, ¿cuánta concentración pusiste?
Sí, de hecho, en el agua gris, pues no teníamos el analito, entonces lo tuvimos que suministrar. Y pues nada más medimos lo que fue la DQO, que teníamos un valor inicial de 551, y pues se removió en 33%. Pero como tal, no dimos como el seguimiento a la indometación.
Okay.
Gracias por tan interesante presentación que nos diste. Lo que entiendo en tus resultados es que en tus efluentes tratados pues al final las plantitas crecieron menos. Entonces, bueno, ya nos daban esos datos y sí son diferentes, pero al día de hoy, ¿qué modificarías para tratar de resolver eso, no? O sea, remueves algo del contaminante, pero tienes problemas con crecimiento de vegetales. ¿Qué harías? ¿Cómo lo resolverías?
Pues es que como tal, ahí a lo mejor hubiera sido bueno hacer como un estudio más de citotoxicidad para ver como bien a nivel celular qué es lo que pasa. Porque, por ejemplo, la indometacina lo que hace es modificar los estomas de las plantas, pero en cuanto aquí, pues me imagino que es más por la cuestión de las especies radicalarias que pues quedan, ¿no?, remanentes. Y podría ser a lo mejor más tiempo de mineralización o algún proceso alternativo.
Okay, more questions and commentaries for me. Professor Erika, over there.
Pues muchas gracias, está muy bonita tu investigación y sobre todo todo lo que cuidaste a nivel estadístico en estos procesos, pues sí es súper importante. Justamente de la última pregunta que te hicieron respecto a que en lugar de que creciera más, disminuyera, ¿tú sabes qué características debe de tener el agua para que crezca el frijol? ¿Es apropiado el frijol para crecer en este tipo de agua?
Pues me parece que son como requerimientos básicos. Por ejemplo, en el control solamente pusimos literal agua, sin ningún tipo de nutriente o algo así. O sea, solamente fue germinación con agua, pero pues sí sería...
Porque a veces es como una sugerencia, ¿no? Porque a lo mejor está como muy bien desarrollado el trabajo y quizás la especie vegetal no sea la apropiada para comparar este tipo de... O sea, la calidad del agua. O sea, es sugerencia, ¿no? Gracias.
More commentaries, questions? Over there. Thank you.
Justo nada más, bueno, gracias por la presentación antes que nada. Justo nada más para ayudarte a lo mejor a responder esto último que te cuestionaron. Durante la plática en la mañana comentaba que tuvimos nosotros también un problema similar con lo del crecimiento con la lechuga sativa. Es muy probable que el persulfato y varios de estos que generan, bueno, de estos tipos de oxidantes, degrade el contaminante a ácidos carboxílicos. Entonces, esos ácidos carboxílicos muchas veces no son tóxicos, pero cualquier ácido va a inhibir el crecimiento de casi cualquier planta. Hay por ahí un review que habla sobre eso. Entonces, por eso se recomiendan pulgas de agua para hacer este tipo de seguimiento, ¿no? El Bifibrio fischeri o Daphnia magna. Gracias.
Gracias.
Okay, another question over here. Allow me.
Que de hecho detrás se me puede comentar, pero la parte de la germinación la hicimos en caja Petri y la parte ya del crecimiento la hicimos en pitmos con abono, así me fue el nombre, suelo, que tenía 30% nitrógeno y bueno, los requerimientos como comunes del suelo.
Gracias. Igual para complementar relacionado a las pruebas de fitotoxicidad, o puede ser lo que mencionó aquí el compañero, o puede ser que, aunque tu tratamiento también fue muy bueno, la concentración que queda residual, esto está por encima de la concentración como letal de tu especie también. Pudo haber sido eso. También que, aunque alcances eficiencias muy altas, pero como la concentración letal está más arriba, pues nunca vas a poder evaluar bien esa parte de la fitotoxicidad. Habría que revisar exactamente cuál es el organismo vivo que queda para tu prueba también.
Would you like to ask the question or not? Okay. Okay, thank you very much for your presentation. Okay, and now we have the talk from Erika Axel Garcia Garcia. which is entitled Modeling and Box Banking Design Optimization for the Efficient Removal of Ibuprofen by heterogeneous phantom-like reaction using an hematite or magnetite HNTS as a catalyst. So go ahead, please.
Thank you very much. Thank you. I'm very glad for be here and present my research work. And thank you, of course, for your attendance. My name is Eric Garcia. I'm currently studying the PhD degree. I'm going to present my master study. Okay. Headliners in this presentation is related to introduction. We're going to talk about the emerging contaminant. Even I want to talk about the ibuprofen, which is the contaminant where I pretend to degrade. I'm going to do it with a nanocomposite. I'm going to use nanomagnetic and halloysite. I'm going to talk about the synthesis of the magnetic nanomaterial. Then I'm going to talk about two experiments. In one side is the absorption process, and the other side is the phantom process. And then I'm going to talk about some of the morphology of the nanomaterial and the results of. I'm going to use I used a responsive surface methodology, a Volkswagen experiment for analyze the results and explain the elimination. Okay, the problem here as a contaminant emerging that is very common nowadays in the environmental. It is used most frequently over the years. So it is it's a problematic because this material is very harmful even for the environmental source as human. And this kind of pollens are included in all life cycle as a human process and the animals and the environmental. So that's why it's very common that it is pollen is found in many in all the environmental. So okay. This contaminant, it's a lot of it's produced because of the human production. The most common are the personal care products, creams, sun cream, pharmaceuticals, antibiotics, pesticides. So as you see, all this material is because of the human activity. In particular, in this presentation, I want to talk about the pharmaceutical. The most common pharmaceutical is the metformin, ibuprofen. So that's why it's a real problem. As you see, this material is very stable because of some have aromatic rings. So that's why it's very frequency in the environmental, and that's why it's very hard to remove. Why ibuprofen? The ibuprofen is after the metformin is one of the most common pollens, which has been found in a lot of environmental. I made this map, which it is found in practically in the whole world, and it was studied about a concentration of 40 micrograms per liter. It is necessary for be a danger for the ecosystem. It's very dangerous for all these animals. It is found that it's dangerous, yes, for all this kind of fish. So as you see in those studies, it is used 14 micrograms per liter. And here, even in a lot of countries, we found even 325 micrograms per liter. So this is most of the required for be dangerous for the environmental. And why this nanomaterial? So my aim in this work is use a phantom process to the mineralization of ibuprofen. So I choose magnetic because it has iron oxide, which is uses for the phantom process. And this is the structure of the magnetic. It's a sphere. So I'm going to I use alusite nanoclide as a catalytic support and even for absorption process, because alusite has found that it's very useful for absorption process and it's very stable and it's a natural clay. So that's the reason why I want to combine those materials. So even more, these materials are not toxic, not corrosive, are easy to use and easy to synthesize. It's reusable, low cost, and it has magnetic properties, which when I apply a magnetic field, it is easy to recover. So it is easy because I can use it and then recover easily by a magnetic field and reuse again. Okay, the materials and method. This work consists in three parts. One is the synthesis of the composite, which I use a co-precipitation method using iron oxide in presence of a basic medium. It is easy to synthesize magnetic. So I synthesize magnetic and I synthesize the magnetic support on the alusite. So the next part of the work is the using of this material to analyze how could be the ibuprofen absorbed onto this material. And for this, I use a design expert program, which it helped me because I use a statistic methodology in which I modify every variable. And it is useful because I can find which is the best condition for the absorption. And then the third part of the work is the mineralization part by phantom process. The same, I use a statistics process to analyze each variable. And this is a monitoring design. And then I use a box Beighton design to find the optimal condition for the mineralization. And this it is measured by chemical oxide demand, and then for total organic carbon and HPLC coupled with mass. For the part of the characterization, I synthesize this material. In this part, we can see the magnetite. As I say, is a spherical molecule. So it is very common that this material is agglomerate. So it is a problem because it's a little more difficult to use for separate. For that reason, I use the alusite because it is support on the nanotubes. Is the alusite, and here's the magnetic, which it is used because it is evade the agglomeration. And then I analyze as EDC to confirm the presence of iron, oxide, silicon, aluminum, and by XPEs for analyze the composition of the, to be sure that all the materials are present in the nanocomposite. Then I use a bed method to get the superficial area and to find the diameter of pore. And even more, I use the X-ray diffraction to be sure that all the signal of the magnetite, the hallusite, it is present in the material. So in this result, I can see that the magnetite have a stericity 1, that this is common in agglomeration and spherical particles, and the hallusite have a stericity cycle of H3, is characteristic of materials with laminars and uniform shapes. So yes, and I analyze this with UV spectroscopy, I quantify the initial concentration of ibuprofen and the final concentration, and using that, I evaluate the ibuprofen absorb 22 nanometers, is the high absorbance. So as I say, I evaluate the pH at the absorbent dose, evaluate how it is could be more useful to how this variable help me to find the optimal condition. And it is very useful because this statistic models give me an empirical equation that describe the quantitative the method, and it give you a value which I can compare for every experiment. So here I found that the best condition for the absorption, it was a pH of 2 and a concentration of absorption of 1.5 gram per liter. So even this is not a good result because the most absorbent quantity of even absorbed, it was around of 10%. Really, this was very low because, well, compared with another techniques, with another materials. But this is important to know the exactly quantity, the material that is absorbed, and which is, because we want to know which quantity of material is absorbed and which quantity is mineralized. So even more the absorption provide the mineralization is better that the material is absorbed on the material. And once I found the optimal condition, I made some models for the absorption for kinetics. This experiment I used to Frank-Lewis isotherm and pseudo second order isotherm absorption. And this is characteristic for heterogeneous physical absorption in multiplayers. And this is characteristic of absorbing with abundant active site. It is useful because it could provide the information about the pathway of the absorption. So as I found, as I say, it's a low concentration, a low absorption, and as I say, it's physical heterogeneous absorption. So it is suggests that the absorption is going through a hydrogen bond. Is the reason why it's very weak and why it's not very useful. But well, this kind of experiment could describe that process. And then I compare the result with another work. As I say, it was a really low quantity absorbed. It was around 5.1 milligrams per gram, compared with another materials, which is the carbon nanotubes, that is around 81. But this is important to know what is the exact quantity of ibuprofen that it is absorbed, which is mineralized. Because why maybe I can start with the phantom process, but I don't know if really the material is mineralized or the material is absorbed in the nanocomposite. So that's the reason why is this the absorption study. Then I moved to the heterogeneous phantom reaction, the mineralization. So again, I use a statistic model. At first, I use a monitorial design, which I use this variable, the pH, the peroxide, the hydroperoxide, and my absorbent. So I use this concentration because of the reference. So it is very useful because with a few experiments, it gives you a lot of information of what kind of pathway could be best and how I could modify the quantity. I improve the mineralization. So in this study, give me the Pareto plot, and it even more the equation, the empirical equation for this method. As I say in the Pareto plot, the pH is the main variable to the absorption. It is blue because it means that it must to be reduced to to improve the absorption. Which means that it works better with acid condition. And then we have the absorbent material. And the useful of this kind of statistic method is not just analyze the every variable, if not that analyze the variable combined by itself. For example, AC, it means that this is a combination between pH and absorbent material. It means that as the absorbent, it is affected by the pH because it could be protonite. So it's why it's present here. So it is means that it tell us that for a better absorption, the nanomaterial must to be protonite in the acid system. So it is the advantage of this kind of model, and it gives you a superficial methodology response. It is show the tendency of how I can use each variable to improve the absorption, the remove. For example, here it is said that I can increase the quantity of absorbent to improve the mineralization. It is the use of this kind of study because with a few experiments, I can reduce the doses of each variable, and for that I can use a better experimentation. And based on the previous result, I use some quantity. I use the pH to 7 because the aim of this work is work in a neutral condition because it's better for previous treatment. And yes, and I modify the quantity for hydrogen perox and absorbent. So which is I use a little more to see what happened. And the importance of this kind of plot is to find the curvature, to find the optimal condition and not find just the tendency, because I can using more and more and more, always is growing, but it is find a level that is not more useful. So with this table, it is give me the optimal condition for the Evo remotion, which is in around the doses of peroxide is 0.5, and the doses of catalysis is the 1.5 grams per liter. So once this is the result I measure with the BQO. So once I found the optimal condition, I use those conditions for be sure with another measure. I use COD to find the mineralization, because this just gives you the oxidation of the ibuprofeno, but don't tell you the quantity of mineralization. For that reason, it was used the COD, which it found that the ibuprofeno was mineralized about the 60%. And even more with this condition, as same, I use a HPD analysis to find why can the exactly amount of ibuprofeno which is degraded, and if it is mineralized or not. So I found a mineralization of ibuprofeno at this condition about this. Well, the oxidation was around the 90%, but the mineralization was about the 60%. And I compared with another work with this is use a similar nanomaterial, and I have a good result around the more than 90%, which I think that's good result because I'm working in neutral condition, and the most majority of the work work in acid condition. So I think this is advantage for this kind of material and this kind of method. As a conclusion, in this study, it will be possible to synthesize a magnetic composite which have the property to, as a catalyst, as absorbent for the elimination of ibuprofeno, more as a catalysis. I found the optimal concentration for the absorption. As I say, is not a big quantity, about 5.1 milligrams per gram. And finally, I found 98% of EVO removal and 60% of mineralization in the optimal condition. This work has been published a month ago, the 15th May, and I want to acknowledge to the PAPIT program and of course of you present here. This is the work team. This is the Dr. Yolanda Marina Vargas, which is my tutor. And this is where we work on Facebook Titlan. And this is our lovely lab, which I work. And that's it. Thank you for attending.
Okay, thank you for the presentation. Very nice research. Okay, some questions from the audience? No? Or your type? No, okay. Allow me.
Well, first of all, congratulations for your exposition. About your experimental design of the oxidation process, specifically the one of response surface, which will be the most significant factor of your experimental design, and how can you increase the degradation of the ibuprofen in the media? And well, that's it.
Come again?
Well, again, is about your experimental design of oxidation of ibuprofen, which will be your most significant factor, and how can you increase the degradation of ibuprofen?
Well, at first, I think that the most used, the variable that is very affect the phantom process is the pH. I think that it could be get a better results using an acid condition because it improves as the absorbent quantity and improve the mineralization. However, I choose to use the pH 7. That's why this is I try to increase the quantity of peroxide and the catalysis, especially for that, because if I reduce the pH, if I use the pH neutral, it is logical that I obtain a less mineralization. However, this is why I increment as dose for promote the mineralization at that condition. But yes, I think that the pH is the most important variable here because it affects on the whole system. It affects the peroxide, it affects the catalyst, and of course, for that, it affects the mineralization.
Okay. More questions? Okay. Tell me.
Thank you. Great research. First of all, I have two questions. You said metformin is higher found. Why didn't you research the effects of metformin instead of ibuprofen?
Yes, metformin is most frequently found in the environmental. Here I have two options to work in the metformin and work in the ibuprofen. The ibuprofen is a little more easy for the mineralization, and metformin, because of the presence of nitrogen, and it's a very small molecule, based of the reference, it is more difficult to mineralize. With this process, I think that it is not possible to eliminate the metformin. I want to find for the ibuprofen, which I have a good result. But yes, my PhD research is about the metformin, and I want to apply this methodology. I want to apply with another. As we say, phantom process have a lot of use. We can promote the use of phantom with another energies like electrophantom, photophantom. the goal of my PhD research is exactly promote the photophantom with this material, coupled with oxide of titanium. I'm working with the three materials. I try to make an nanocomposite with the three compounds. And yes, it promote the mineralization and be a better, more powerful for the elimination of metformin. And yes, it will be used for this, for ibuprofen too, but yes, the metformin is a little bit difficult to remove than the ibuprofen.
Okay, so that's my second question. Actually, would you expect, or are you expecting some good results in your actual investigation with metformin using this? How do you call it? Name it. This composite.
Yes, it's the magnetic support on hallucinated tubes. Yes, I hope that, as I say, metformin is a little more complicated to eliminate. So it is why I try to couple to another system. I want to use a photofen, heterogeneous photofen process. So yes, I hope that I found an optimal condition to be removed that material. But yes, is my challenge that currently I have.
Yeah, thank you.
Thank you. More questions? No? No? Okay. So this is the end of all the presentation in this day. Thank you very much for the presentation, Eric.
Thank you very much.
And also thank you to all the audience connected in the social. We see you tomorrow. Thank you very much. See you. Bye-bye. Y nosotros nos quedamos aquí. Les doy algunos anuncios